Hi, everyone. Welcome to the Waterloo Artificial Intelligence Institute seminar series. I think we're series instance 3 or 4 here today. And today we're very happy to have Professor Graham Taylor from University of Guelph going to be giving us a talk. So I'm going to introduce him in a minute. But before I start, I just want to take a few moments to honor the passing of a former Dean of Engineering here at University of Waterloo, Pearl Sullivan, who was the Dean of Engineering here from 2012 to 2019, passed away on the weekend after a battle with cancer for 12 years while she was Dean. And she was a beloved dean here in the university, and was really pivotal for a lot of the things that have happened recently here, including the creation of this institute. And some words from our current dean, Mary Wells, saying that she was a force of nature, always fearlessly working to advance Waterloo engineering and opportunities of our students and faculty, a compassionate and caring leader who would rally her team to the causes that would matter most. She's irreplaceable, and the memory of her personal strength will always be a beacon of courage for us all. That's from our current dean. Yeah, and her passion in supporting students to reach their full potential engineers kind of guided everything she did. And she was like well known for being passionate and hardworking and enthusiastic for moving the university towards new innovative programs of research, including artificial intelligence, advanced manufacturing, nanotech, robotics, wireless communications. And she was so hardworking, you'd often bump into her. Like, I was going to a conference once in Asia a couple of years ago, and for me it was a big trip over for this big conference. For her, it was a Wednesday on a flight to Asia, drumming up more money and connections for research for the university. So she just never stopped, and it's a real loss for the university to have someone such as her kind of gone now. She also had a very deep excitement for the promise of artificial intelligence and helped create this institute. It was really central to creation of it. And so from the AI community of Waterloo, all our thoughts and best wishes go to Pearl and her family, who are having her service today. And I'm sure she'd be very excited about the things that are happening here and the stuff we'll be talking about today as well. So just want to give a moment to honor her. So thanks for that. So today's talk, I'm sure she'd be very excited about. It's Graham Taylor, just from down the road, University of Guelph. He's on campus often on committees and various things here, so we all know him well. He does fantastic research into artificial intelligence and machine learning. Professor Taylor is a Canada Research Chair, an Associate Professor of Engineering at the University of Guelph, the Director of the University of Guelph Center for Advancing Responsible and Ethical AI. He's a member of the Vector Institute, a CFAR Israeli Global Scholar, and a CFAR AI Chair. He's going to be telling us about today conditional generative adversarial networks, which are very exciting kind of technology, and some of the work he's been doing with them. So just logistically, there is a Q&A box on the side as you're watching this live. This will be recorded as well if people want to watch it later. But if you have questions along the way, just post them into the Q&A and I can forward them to Graham as he's talking or in the breaks. We also have time afterwards to kind of have questions back and forth. So without further ado, take it away, Graham.
Okay, awesome. Thanks a lot, Mark.
Stop sharing my screen. There we go.
So, Mark, do you see my title slide?
I can. 15 years of conditional
Okay.
generative. Yep.
I changed the title of everybody to make it a little bit more accessible.
Our website you can't do that. Okay, that's fine.
So, yeah, I did want to say a couple words about Pearl. It's interesting that Mary described her as a force of nature, because I was also going to use the word force. I thought she was a dynamic force, and I really appreciate that she took the time to get to know me and my group, even though we're based in Guelph. And Pearl also served on Vector's board. So she really was key to building links between various universities and institutions. And it's a pleasure to have gotten to know her. I also, while I'm really saddened by her passing, I know you're in great hands, because you have our former dean of our college, Mary Wells, to lead your faculty forward. So anyways, it's bittersweet. It's a sad day, and I know we were sending some emails back and forth last night to decide whether even to go forward with this talk. So ultimately, we decided to do it, and given that Pearl was interested in AI and has done so much to amplify the already existing great AI efforts going on at Waterloo, I think it's fitting that we do this talk today. And I know that some of you, or many of you, will be grappling with what happened. So so I'm conscious of that. So the reason why I had decided to change the title of this talk is because I was reflecting on research going back to being a PhD student at University of Toronto. I was an undergrad and master's student here at Waterloo, and I came to the realization that I had been conditioning generative models for 15 years. So what does it mean to be a generative model, and what does it mean to condition? So in machine learning, we're usually concerned with making predictions, often with probability distributions of the form P of Y given X. And so here, X is often some high dimensional complicated quantity, like an image. So for example, in an image classification setup, and Y is often simple, like a label. So generative models, on the other hand, they instead focus on modeling a different distribution, a much more complicated distribution. So they model P of X and Y, the joint, or they marginalize over Y and model P of X. And so now you notice that the distribution is on the high dimensional complicated quantity. I'm being pretty general in all of this. Of course, there's other types of predictive models like structured output where you are modeling high dimensional quantities, but I'm keeping it sort of simple and general to nail down the key points here. But one of the key points is that generative models have a much more complicated problem to solve. There's many reasons for this, but one reason is because of the nature of X being high dimensional. And this is a very difficult optimization problem in some ways. And also, there are many right answers for generative models. And so we'll talk about that shortly. So in prediction, there's often a single right answer, like you're trying to predict the temperature tomorrow, you're trying to predict a future stock price, and there's ground truth for that. But in generative modeling, there's often, there doesn't exist the same kind of ground truth. And so it's a difficult problem, but it has many applications. And so the final point I want to make, and key to a lot of what I'm going to talk about today, is that we can often control the distribution of a generative model. So we can condition on some additional context or information. Why? So we can condition on a label. So we can generate, say, images of different classes. We've seen many examples of that. We'll see more today. We can condition on text. We can condition on different attributes. And so conditioning can make our generative model much more powerful, and we can control it, as I point out here. So one of my favorite examples of conditioning generation is the autocomplete as used on my Android phone. Many of you are using such devices, and like I said, we're creating high dimensional input or output, and the input here that we're conditioning on is the text that's been typed so far. And then in this example, you can see that there's many correct answers given the starting point of a sentence. And so hopefully it's clear what I mean is there's many correct answers for training a generative model like this. And so other examples that exist are in image and speech and text synthesis, image to text, text to speech, and as we see here, this is a text-to-text application. So we'll see many different examples later on. So I mentioned that I had been doing this for a long time. So during my PhD, I was working on generative models of human motion. And these were conditional models because we were conditioning on a style variable. So we had a dynamics model, which would generate joint angles over time. There's about 30 variables that are being produced at every time step here, corresponding to joint angles. And then what we're doing here is we're changing the style label that we're conditioning on. So you can see here 10 different styles of walking. And this model does real-time synthesis. And again, coming back to this point of being difficult to evaluate, I mean, the motion coming out of this model looks to me still to be fairly realistic, but there are some artifacts. You can notice that the feet are skating a little bit. This was always a problem in this model. And that is something that has always been difficult to evaluate. We evaluated these models by predicting forward and almost treating them like a forecasting model, but that doesn't highlight sort of the perceptual nuances in the creation of this data. So it's still evaluating these generative models is a outstanding question. Take it forward a few years. This is another model that we subsequently developed where the mechanism of conditioning is more complicated and more interesting. So instead of really appending a series of style variables and additively connecting them into the dynamics model, we actually had these style variables project onto a series of latent factors and have them control the effective weights of the model. So this allowed us to do things like blend different styles together. And as we changed the value of these variables or blended them over the course of the motion, they would change the weights of the dynamics model, and you could have very smooth transitions from one style to another style, even though there were no blended styles in the data set that we learned from, and there were no transitions. We only had examples of individual types of motion. And so this is really interesting to us because we were effectively extrapolating here. And you've probably heard neural nets are good at interpolation and not so good at extrapolation. But here is a case where we are very much doing generalization far beyond what was in the training database. So, okay, fast forward to now, people are very interested in generative models. And I'm going to talk about a particular type of generative model called a generative adversarial network. And Ian Goodfellow has a great tutorial on generative adversarial networks, and he has this nice list of why we might need generative models. So, for example, in applied math and engineering, which is very prominent at University of Waterloo, we can test our ability to build and use high-dimensional complex probability distributions. So we can pipe these high-dimensional distributions into other areas of science and engineering. We can also take generative models and incorporate them into planning and reinforcement learning. So I know Mark, who introduced me, has been working with some students in doing reinforcement learning. There's a lot of activity in this field at Waterloo and in other places. And many people are interested in what's called model-based reinforcement learning, where we can augment the agent with a model of the world. And so the model, again, it's a probability distribution of the plausible states of the world. And we can use conditional models of the sort, if I do this, this could be what happens. And this can play a huge role in making learning more efficient in reinforcement learning. Generative models allow us to handle multimodal outputs. This is we can have one or many-to-many mappings. So again, this is going back to my comment before. There's many possible correct answers. So we've used this in robotics, where we're planning grasps, and given a visual input, there might be many good grasps corresponding to that visual input. And so generative models can be useful for sampling multiple grasps and evaluating them as opposed to just predicting a single correct grasp. And then we can also use generative models to fill in inputs that are missing in data sets. And then finally, what I'm going to show a lot of today is realistic generation, like the synthesis of motion sequences I showed before, and then the image-based applications I'll show later. So not on this list is another property of generative models, which I've been thinking about quite a lot lately. And this is that these latent variable models provide a complete, or so I say complete in quotes, description of data. We don't have just the data example, but we have a series of latent factors that describe how the data was created. And by performing manipulations or optimizations in the latent space, we can achieve various artistic and creative applications that would not be possible just from the data alone. So here's an example I'm showing you from a recent project with Modiface, a company in Toronto, who do computer vision for the beauty industry. And this is a GAN-based technique to perform hairstyle transfer from one person to another. So hopefully you see my mouse. Mark can let me know if my mouse is not visible. Mouse is not visible?
Not visible, no.
Not visible. Oh, that's too bad. Okay, I can see my mouse.
If you go over the picture, I think I saw it for a second. Yeah, it is. Just if you go slowly, we can see it.
Oh,
yep, there, I see
okay.
it. Yep.
Perfect. Okay, so I'll use a slow mouse. So you take this individual here, and you provide some examples of, say, this person with red hair. Say we want their hair appearance and style. And then this other person, we want their hair shape and structure. And so this is the mask below of the hair shape and structure. And by having this set of variables which describe how this original image may have been created by a generative model, we can apply the desired hair color and appearance and shape to the original target. And then again, by inserting different examples, as you see in the next few images, we can do realistic hair transfer onto our original subject. We have another subject at the bottom, again, where we're, in this case, maybe only manipulating, for example, the shape and style, but not the color and appearance. And so this is a recent project on generative models. So I want to reflect briefly on a talk that we had at the Center for Advancing Responsible and Ethical AI almost a year ago now, where Jutta Treviranus came from OCAD University in Toronto and spoke to us about inclusive design. So she talked about this 80-20 principle, and this is something that it stuck with me because I've actually taught on this in software engineering. So this was taken by software engineers to take Pareto's research and sort of warp it into this message of, if you want quick wins, ignore the difficult 20% of customers who take 80% of the effort. And this has been sort of a mantra in software engineering. And Jutta has argued against these ideas. She's not just argued against Pareto. She's argued a number of other scientific and philosophy figures. But her main message in talking to machine learning people is that machine learning works well for the average, because that tends to be where we collect our data. But it doesn't work well for everyone. And so one direction we can go is that we can work towards building machine learning systems that work for everyone. And that is something we're trying to do at Care AI. But a different direction we can go is approaching more inclusive design using generative models. So I certainly think that we've reached a new age of personalization, and we're seeing this in many applications of AI that build customized solutions for individuals. Many startups are working in this space. And this sort of hyper-personalization space, in some sense, allow conditional generative models to lower the cost of custom design. And so we've seen examples of generative models creating a wide variety of digital artifacts like images and videos and text. I'm sure many of you have seen the output from the GPT-3 model at OpenAI. And these are being used in digital design. And to some degree, generative models are being used in physical design as well. So in computational chemistry, and material science. For example, there was a big announcement yesterday all over the news about DeepMind's work on protein folding. However, generative models have been less prevalent in architecture, landscape design, and manufacturing. There was a talk at BMO Center for Art, AI and Creativity in Toronto on last Friday about the use of generative design in architecture. But really, this is at the level of having conversations. We're not seeing a lot of machine learning paper focus on these sorts of topics. And so can we use generative models to, again, lower the cost of customized design so that we have objects in our physical space worked better for marginalized groups, the elderly, the young, the physically and mentally disabled. And while we're far from achieving this, we're taking a step in that direction by teaching generative models to build Lego. And so this is moving generative models into the physical space. I'm really excited about this work. This is a generative model that's based on graph structured neural nets, and it learns from human-built structures to create. Again, it's being conditioned on classes of objects. So here you see it, if it's conditioned on a wall, we can sample a wall. If we condition on it to build a line, it can generate a line, or an object class called cuboid. It will generate these flat structures. And when we look at some of the samples that are generated by this model, it's remarkable it's remarkable what it learns about symmetry in the construction just from several hundred examples. And it's not merely duplicating what's in the data set. We can compare each of these samples to their nearest neighbor in the data set. And the walls, for example, that the model is generating is much longer. The cuboid has this this hole in the middle of it, and there aren't such objects that exist in the training data set. So this is something that we're presenting at a NeurIPS workshop actually this month. It's already December. Okay, so while like I said, I'm very excited by moving generative models into the physical space. For the remainder of the talk, I'm going to head back to the land of digital artifacts. And so I'll focus the rest of the talk on a particular type of generative model called generative adversarial networks. I'll do a quick review of these. And then I'm going to talk about three different limitations and then solutions that we've proposed in the space of conditional GANs. So I'm going to talk about a generative neural visual artist. I'm going to talk about evaluating these conditional GANs quantitatively. And then this wasn't in the abstract I sent, but it's sort of late breaking work that's being presented at NeurIPS in a couple weeks on doing instance selection to train GANs more rapidly, but also reduce the complexity requirements. So I'm sure almost all of you at the talk have seen a picture like this. The outline of generative adversarial networks. This is sort of the classic story of the counterfeiter and the police. So you have a generator network which is trying to generate very realistic data. You've also got a data set of real images, and so the real images and the images coming from the generator are being fed into this other network called a discriminator. So this is like the police network, and it's looking at the two types of data that are coming in, and it's a binary classifier that's saying whether the data is real or fake. And the idea is that from the discriminator's point of view, it wants to call the real images real and the generator's images fake. But from the generator's point of view, it wants the discriminator to call its generated images real. And so the idea is that there's this two-player game where the generator and discriminator will ultimately settle on a solution where the discriminator is unable to tell the difference between the real data and the generated data. And so less talked about beyond the story of the counterfeiter and the police is this other story about this being such a beautiful formulation because you don't have to write down an objective of what it takes to make a realistic image. And in predictive machine learning, we've gotten very used to not writing the rules down to make a decision, right? So if we do face detection or face recognition, we don't have to write a program of what it means to be for your face or a program to recognize my face. I mean, that's essentially what machine learning is all about. GANs really go further in optimizing and automating the machine learning pipeline. They allow this kind of dynamic objective as a discriminator adapts to the attempts of the generator to make the images more realistic. It improves its ability to detect artifacts produced by the generator, and this objective is effectively dynamic through the course of training. But again, dynamic and implicit. It's not written down anywhere. And so we can introduce conditioning into GANs by providing some conditioner context. So for example, a label into the generator. We often will provide it into the discriminator as well. And the context might come in the form of a bounding box as well, or a segmentation mask, coordinates, or it could come in the form of text. So most works out there, including vanilla GANs, generate these images in a single step. And so ultimately, what we're interested in doing in the first series of work I'm going to talk about is that we'd like to do interactive synthesis, where the image being generated is iteratively updated based on ongoing linguistic input or feedback. So again, not one-shot generation, but an iterative process. And this could make existing digital graphic design tools more accessible, particularly for users with impairments. So imagine like basically an interactive Photoshop. So there is already a large body of work on generating images conditioned on a caption. This is known as text-to-image synthesis, and this includes GAN-style models. But typically, these works are just one-step generators. They're not iterative or interactive. There are multi-stage GAN models. So a notable example is StackGAN, where you have a first stage generating low-resolution images that are conditioned on the caption, and then a second stage generating a higher resolution image, which is conditioned on the previous image and the caption. But despite this model being multi-stage, I would still argue that the caption is received in a single shot. It's a complete description of the image. It's very far away from this goal of continual linguistic instruction. Another model called Attention GAN builds upon StackGAN by introducing an attentional generator network, and this allows the generator to synthesize different spatial locations in the image, conditioned on this attention mechanism over words in the caption. And moving away from just captions, our collaborators at Microsoft Research Montreal proposed a non-iterative model called Chat Painter that generates images using dialogue data. And so Chat Painter conditions on captions from the MS COCO dataset and an RNN encoded dialogue relevant to the caption. And so that's what you can see on the left. The dialogue is between a pair of individuals that has been captured on Mechanical Turk doing a question and answer about the image. And so Alla, the main author of the work I'm going to talk about, was really inspired by Chat Painter. And this actually sparked his interest in going to MSR to do an internship. And in this Chat Painter work, the authors showed that Chat Painter was able to generate superior images than just using the captions alone. But again, it's not really interactive, it's not iterative. The model reads the entire dialogue and generates a single final image. And so this certainly differs from this idea of having, say, a sketch artist, where the artist has to keep making changes to the current sketch based on feedback. So that's a bit of background of what's taken place before our work. Now I'm going to get into our actual model. And this is really a different kind of task. And so we call it the generative neural visual artist, and we propose a specific GAN type model for this task. And the way this task works is it's all about gradually transforming a blank canvas to a scene. So at the top, I'm going to move my mouse around slowly. We have an empty canvas, and we model an interaction between a teller and a drawer. So the teller is giving an instruction, like here, add a yellow sphere at the center, and then the drawer puts the yellow sphere on the canvas. The teller observes how the image has changed, gives some additional instruction, add a purple cube behind it on the right. And notice that we're referring to the last added item as it. And so the drawer then needs to take that information from the teller and add the purple cube and so forth. So it's an iterative process where an image is incrementally composed as a sketch artist would do. And so some of the challenges associated with this new type of task is that the drawer needs to learn how to map complex linguistic instructions to realistic objects on a canvas. And so it needs to not only maintain the object properties, but also the relationships between objects. As you could see in the instructions here, we're speaking about relationships, in front of, behind, to the left of, and so forth, these different objects. And the drawer also needs to modify the existing drawing in a manner that's consistent with the previous images that have been composed so far and the instructions that have previously been given. So it needs to remember previous instructions. So you have this notion of long-term temporal dependencies. Okay, so this is a reasonably complex model and probably the most complex model I'm going to chat about in this entire talk, but I'm going to walk by it step by step, and I'm going to go through the model architecture in 2 stages. So I'm going to first explain the generator. Again, it's a GAN-based architecture, so you've got a generator and a discriminator. And so starting with this generator, the generator is provided this empty canvas, and it's got a list of instructions. So the instructions here are marked as Q. Okay, and so then the teller provides, for every turn in the conversation, the condition generator is going to output a new image. So I move my mouse over again, so you can see G is a generator and it's outputting an image. And this is X tilde. And there are several variables that are being fed to the generator. So we've got Z, the latent variable or noise vector that's present in all GANs. We've also conditioned the generator on 2 additional variables. We've got HT and we've got FGT minus 1. So H of T is what we call a context-aware condition. And this encodes the information that's coming from the language instruction. And then we have this F of GT minus 1, and we call this the context-free condition. And so the context-aware condition needs to have access to the conversation history so that it can learn a better encoding of the instruction in the context of the conversation history all the way up to T minus 1. So each instruction, Q of T, is encoded using a bidirectional GRU on top of glove word embeddings. And so the instruction encoding is denoted D of T. Okay, so here we have a GRU that's taking the instructions, like here, the mad boy kicking a ball to the left of whatever. This is being encoded through a GRU into D of T. It's like an embedded language. And then we have a second GRU called R, which is operating on the context-aware conditioning. So note that there are basically 2 GRUs, one separate from the model and then one operating on the input to the context. And so we've also, this context-aware condition is basically the modifications the teller is describing in the new image. And then this context-free condition is an encoding of the previously generated image, which we see at the top right here. And it uses a CNN convolutional neural network based encoder. So this context-free condition represents the prior that's given to the model by the most recently generated image. So in other words, it's a representation of the current canvas. Okay, so that is basically the generator. I want to point out two different timescales. There is a timescale at the level of the word, so that's the 1 GRU, but there's also a timescale at the level of instructions. So those two different GRUs are operating at two different timescales. And so what you're seeing here in terms of the model, it's operating at different steps of the generation process, not at the steps of the words coming in. Okay, so let's now talk about the discriminator, which is the upper portion of the architectural diagram. So since we're modeling iterative modifications of images, it's insufficient to have the discriminator simply distinguish between real and generated images at each step. So the discriminator should also identify cases where the image is modified incorrectly with respect to the instruction or not modified at all. So we have to introduce 3 changes to the standard GAN discriminator. Okay, so the first change is that we used an image encoder to encode the current time step image and the previous step ground truth image, and those features are fused and passed to the discriminator. So we use, this is what's happening in this highlighted block here, current image, previous image, and then the context aware condition is also used as a condition for the discriminator as well. So we see this with HT coming in. And then also for the discriminator loss, in addition to labeling real images as positive examples and generated images as negative examples, we add a term to the loss for the combination of real image with a wrong instruction. So it's basically another type of fake data. And then finally, we have an auxiliary objective of detecting all objects in the scene at the current time step. So this discriminator is forced to do object detection, and it makes it more object aware. So that's basically the model in a nutshell. So next I'll mention a few other implementation details. So first, the context-free condition is concatenated with the feature maps from the generator's intermediate layer. So that's happening at this level of the model here. And this has this L of f of g has the same spatial dimensions as this f of g, the context-free information. We also have the context-aware condition h concatenated with the noise vector after applying conditioning augmentation. And so it's used also in applying conditional batch norm to each of the generator's convolutional layers. So that's where the context from the instruction is coming into the generator. We also try concatenation and subtraction as fusion operators for the discriminator. I'll talk a little bit more about how each of those work. But for now, we're going to leave this as a generic fusion operator between the current and the past. And then we also have the discriminator being conditioned on the context by what's called a projection discriminator. And then finally, we have the generator and discriminator being updated every time step, whereas the GRUs and the encoder, so here's one of the GRUs, here's the encoder, and here's the other GRU, those are being updated every sequence. Okay, so let's talk about training the model now that we've gone through its architecture. These models G and D are trained alternately to minimize the adversarial hinge loss. And so what this loss looks like, it's got 4 terms. So the first term is basically the discriminator trying to output real when it sees real data. The second term is a discriminator trying to output fake on fake data. And that's what you're used to in GANs. And then the third term here is the discriminator trying to output fake when it sees real images paired with the wrong instruction. And so we've got some other additional notation here. So CT is the conditioning that's given to the discriminator. tilde-C is the conditioning given to the generator. And then this hat-C down here is the same as CT, but with the wrong instruction. So we've just sort of packaged up some of our previous notation into the C. that holds together all of the contexts under different conditions. And so the final and fourth term in the objective is this auxiliary object detection loss, and that's just a binary cross entropy over all of the n possible objects at each step. And basically, the loss function for the generator wants the discriminator to say real on the generator's fake data. Okay, so that's a complete description of the model. Let's talk about the data that we've used to train and evaluate the model. So for Geneva, we require a data set that contains textual instructions that describe drawing actions along with corresponding ground truth images for each instruction. And so at the time of creating this model, the only data set publicly available is called CoDraw. And so CoDraw has scenes, which are sequences of images of children playing in a park, and there are 58 object types in total. So corresponding to every scene, there's a conversation between a teller and a drawer, which are both Amazon Mechanical Turk workers, and they do this conversation in natural language. So the drawer updates the canvas based on the teller's instructions. The drawer can ask questions as well for clarification. And we treat the concatenated utterances of the teller and the drawer at time step t as the instruction given to the model, and that we inject a special delimiting token between the teller and the drawer so the model is aware of that. And so this is basically what our data looks like. It's a gradual implementation of a scheme that's described by dialogue. And so we also created a variant of the Clever data set specifically for this task, and we called it Interactive Clever. Clever is a popular VQA data set consisting of images of collections of objects of different shapes, colors, materials, and sizes. And because the data set is generated programmatically, this allowed us to basically fork it and create our own variant. And so in our forked variant, each example in the data set consists of a sequence of 5 image instruction pairs, which you can see the form here. And the instruction describes where the object should be placed relative to existing objects in the scene. And so here is the first instruction and the result, next instruction and the result, the third instruction and the result, and so forth. And to make the task more complex and force the model to make use of context, as I noted before, we refer to the most recently added item as it, instead of stating its attributes. And so here we have a 5-step complete sequence from iClever. Now again, this being a completely new task, we also didn't really have an evaluation metric suited for it. So standard metrics for GAN evaluation, like the inception score or Frechet inception distance, they only attempt to capture the quality of the generated images. So they can't detect if the model is correctly modifying the images according to the linguistic input, the task instructions. So a good evaluation metric needs to identify if all the objects mentioned by the teller are present in the generated image, and it should also check that the object's positions and relationships match the instructions. So what we do is we train an object localizer that's based on inception v3, and the localizer produces a set of detections, one for each possible object, and a list of coordinate tuples, one for each object. And so we run the detector on the real image and the generated image at time step t, and we compute precision, recall, and F1 score. And so this object localizer will capture whether the right objects are present in the generated scene, but it doesn't capture anything about the relationships. So we also generate a scene graph where objects are the nodes and relationships are edges, and we can compute what's called relational similarity, where this EGGT is a set of relational edges for the ground truth image when we have common vertices, vertices that are common to both the ground truth images and the generated images. And then we have this EGGGen here on the right, and that's the set of relational edges for the generated image corresponded to common vertices to the ground truth and generated images. So here we're interested in not just seeing if the same objects show up, but if when there are the same objects occurring in the real and the generated images, whether they have the same spatial relationships to one another. And that's computed in this expression right here. So let me show you some examples to make that a little bit more concrete. So here's a closer look at the relational similarity metric. So consider the first case. We've got a real image and then the generative model's attempt to form that scene on the right. And we can see that in this case, none of the correct objects are drawn. Okay, so the recall is 0 because none of the correct objects are present, and the RSIM is also 0 because if the objects aren't there, we can't hope to get the relationships correct. Now in the next image, the second row, the cyan and the gray cylinders are the only objects that are correct. So they're in the ground truth and the generated images. So we get a recall of 40, but there's not a perfect spatial relationship between them. You can see that it's not the same between the cyan and the gray cylinders. And so the RSIM is 0.25. And then in the third case, all of the objects are detected correctly, but some of the spatial relationships are incorrect. So we get a recall of 1.0 and a relational similarity of 0.25. And then in the final image, we get all the objects generated correctly, and they're in the correct relative position. So notice that the images are not pixel perfect representations of one another, but the objects are there and the relationships are correct. So we get a perfect recall and a perfect RSIM. Okay, so because Geneva is a newly proposed task, there aren't really existing baselines which consider this problem and these different data sets. So we perform an ablation study to experiment with different variations of the architecture in order to isolate the effect of each component. So here, each row, like the baseline, mismatch, generative prior, and so forth, those represent different variants of the model. And each column here represents the absence or presence of a different part of the architecture or part of the objective. And so the baseline is the simplest version of the model. So the discriminator loss only includes the adversarial terms L fake and L real. Okay, so we don't have this paired wrong caption with real image. And the generator is only conditioned using the context aware condition, so we don't have the context free condition. It doesn't have an auxiliary objective to do object detection. And finally, it has no access to the previous time step image features. So there's no fusion with the previously generated images. So that's why we have all X's here. Mismatch takes the baseline and it adds the L wrong term to the discriminator loss. So this is the paired incorrect instruction plus real data. The G prior row takes the mismatch model and it adds the context free condition as well as the context aware condition. The auxiliary model, this adds this auxiliary objective of doing object detection. And then finally, we have the complete model with two different forms of concatenate fusion that's happening up here at the discriminator level. So we can either concatenate the history and the current representation, or we can subtract it. And the intuition behind doing subtraction is that we want to kind of force a discriminator to see the relative differences between what was previously there and what's there now coming out of the generator. Okay, so I've left the table explaining the different models or ablations at the top. And now we can look and see how these different variants perform on both CoDraw and iClever. And so there's one additional row here, which is the non-iterative approach. And so this is basically the same model as the mismatch baseline, but all of the input instructions are concatenated into one instruction, and the final image is generated in a single step. And so of all the iterative models, the baseline has the weakest performance because it needs to construct a completely new image from scratch every time step. And so that we see the addition of the G prior shows a stronger gain for iClever than for the CoDraw data set. It's quite a strong gain for iClever, but not so much for CoDraw. And this can be explained by the fact that iClever has much more complex relationships between objects, and the instructions have a strong dependence on the existing objects in the scene. So the iClever model benefits from having access to how the objects were placed in the most recent iteration. So interestingly enough, the auxiliary objective of doing object detection has a different effect on the two different data sets. So for CoDraw, it helps improve recall, and it lowers precision. It also helped relational similarity, as we see over here. But for iClever, it helped improve precision, but it hurt the recall and relational similarity. And so what we think is happening here with this different behavior is that it can be explained by the types of objects that are present. And so while for CoDraw, there are objects that are almost always present, like the girl or the boy in the scene, instead in iClever, there's high randomness in the objects that are present, these different shapes and colors and so forth. And so adding the auxiliary objective encourages the model to make sure the most frequent objects are present, leading to the increase in recall while hurting precision. So giving the discriminator access to the previously generated image helps in almost all metrics. And so we note also that the subtraction fusion consistently performs better than concatenation fusion. That's at the bottom here. And this suggests that encouraging the discriminator to focus on the modifications made gives a better training signal for the generator. So let's see, we'll walk through an example of the CoDraw trained model performing iterative generation. We'll see what it can do. So at the top, we always have the previous canvas. This starts with a blank canvas, and the instruction is below. So the instruction is to add a bushy tree in the middle. And then the next instruction is full sun right corner. Next instruction is soccer ball, bottom right corner. And then next instruction is plane, top left corner. And we see on the CoDraw data set, the model is able to generate scenes that are consistent with the conversation and generation history, and it gets most of the coarse details correct, such as the large objects and their relative positions. And so now we say boy between sun and soccer ball, hands out facing left. It has some difficulty in capturing fine-grained details, such as the tiny objects, facial expressions, like you see the boy has creepily one eye here, and also doesn't always capture object poses. And the model also struggles when you have a single instruction that has several objects at once, and that's kind of rare to have that in the data set. And so that might be addressed by further data collection. Okay, so let's look at iClever. So again, we have the previous canvas starting with the blank one at the top and the instruction below. So we say add a cyan cube at the center, add a brown sphere on the right of it, add a blue sphere behind it, referring to the brown sphere on the left and behind the cyan cube on the right. Add a red sphere in front of the brown sphere on the left and in front of the cyan cube on the right. So you can already see that the instruction in iClever is quite a bit more complicated and the relationships more complicated than in CoDraw. Add a purple cylinder behind it on the left and in front of the cyan cube on the left. And so there we've got the complete generation of the scene. And so the model actually captures spatial relationships and colors very accurately. But in some instances, the model fails to add the fifth object when the image is already crowded and there's no space left to add it without moving the others. And so we don't really have this ability of the model to go back and erase things and make modifications to the scene. Okay, so we've got many other examples from our best model, D subtract, and generally these look quite realistic. We have more examples from the iClever data set. I've bolded here when something goes wrong, but most of the time, particularly when there's not too many objects in the scene, the model basically nails it. Now, if we look at the baseline iterative model, you can tell it's definitely not as good. So this is basically the model without all the bells and whistles, but it's still an iterative model. And this is basically everything ablated out. You can see the scenes are definitely have a lot of artifacts and less realistic. And then we can have the non-iterative approach where we just give a gigantic conversation as a caption and have the model generate the image in a single shot. And you can see it pretty much fails. It's a disaster in all situations. Interestingly, we also experimented with using an intermediate ground truth image as the initial image at test time for iClever, and the model is still able to generalize and place objects correctly into an existing scene. So it's cool to see generalization again far beyond what was in the training set. Okay, so this is a good point for me to pause before going to the next model and see if anybody's got any questions or Mark if anything's up here.
Sure, yeah. Yeah, and we're at 11 o'clock, so we started late in our initial thing. We'll go to 11:30 with your talk and questions, but perfect. We'll know the next one. There were a few questions along the way. I think you answered a lot of them as they were going, like what kind of data is being trained on, like was there supervised data, and you showed that. Somebody had a question about what is the fusion, so I don't know if you're talking more about the fusion methods themselves.
Right. So concatenation and subtraction. So I'll just bring that table back up again. So basically, it's sort of we've got vectors representing the past and the present, and you'll see at the two bottom rows of this table. One is using just simple concatenation, and then the other is using a subtraction. None of the fusion operators were extremely complicated. Obviously, you could insert your favorite fusion operator as well, and evaluate and see how that performs. Sorry, Mark. Any other questions?
I hit mute somehow. My other question, I guess, then was thinking about the scoring of when they're not being perfectly arranged, because it's kind of qualitative arrangement of the blocks, especially, but you were using a kind of exact precision. So is it a pixel thing, or you have a softness for it? You can catch how you're.
Right. So let me go back to the example of the evaluation, which okay, this is probably the best place to stop there. So in terms of precision, recall, and F1, that is based on running an object detector to see if a particular object shows up. So for the case of iClever, that would be like a red cylinder and a blue cylinder would be counted as two different objects. So seeing if the exact correct object shows up. And so that's really like the object recognizer found that it was there in your generation or not.
And they include each other, and that's how you would measure.
Yeah. So is it you have a real scene based on the instruction, then you have your model generating a scene, and you're basically seeing whether the objects were there in the real scene and the generated scene.
Oh, just whether they're present.
Yeah, that's for the recall, and then the relational similarity, this RSIM metric, that goes a step further to then form a scene graph and understand where the objects are, where the detected objects are in relation to one another. And so here, like I think in the third row, this is clear that all of the objects are generated correctly, like they're there. So you're getting a 1.0 recall because they're present in the ground truth and the generated image, but the spatial relationships are not the same between the ground truth and the generated. And so that's why this relational similarity is 0.25 in that case.
Great. Okay, yeah, I think all the questions will work for now. So.
Okay, cool. So I'll do another stop in a bit, and then we'll see if other questions come up from the other parts. Yeah, you know what? I'm just trying to think, because we got started a little bit late, I might jump ahead a little bit to talk about the more recent stuff. And if we have time, we can come back, but I'm just going to make a sort of on the fly modification to the talk. Okay, so I'm going to jump up here. And so I sort of skipped over limitation 2, but that's fine. I'll point you towards the work, and maybe we'll come back to it. So I'm going to tackle 2 other limitations with training these generative adversarial networks. And so these GANs, when tasked to generate realistic images, not like the synthetic scenes I've been showing you, when they're tasked to generate things like the border collie example here, despite considerable advancements, they still generate pretty unrealistic off-manifold samples. So you can see that here, like in the image on the right, in the one in the center, there's some strange sort of framing artifacts. And then the second limitation is that these models are very, very expensive to train. They use a lot of compute. They often take several days, if not weeks, to train. And so the first issue has been addressed, and I'll talk about that in a second. But the second issue is yet to be solved. And so we were actually interested in this work to see if we could reduce the computational burden of training GANs and at the same time improve the quality of generated samples and have less of these sort of spurious examples. And so let me tell you first how people generally deal with the first issue of spurious generated samples. So one option here is to perform rejection sampling by discarding samples which appear to be off the manifold. And so often people use the train discriminator for this. And so anything that the discriminator is calling fake, they'll throw away and leaving the more realistic samples. Another common approach is something called the truncation trick. And this is to manipulate the latent space. And so at training time, you're not manipulating the latent space at all, but at test time, you sort of restrict the latent space from which you sample. And here we're sort of in this video going between sort of a heavily restricted, constrained latent space where all the dogs effectively look the same, like the mean dog, and then we're allowing the latent space to grow as it was during training, and you'll see a fair amount of diversity. So you can basically trade off this diversity versus fidelity by restricting the latent space at test time. So both of these approaches fall into this strategy of train your model and then reject generated samples that don't meet some kind of condition. And so they're effective, but they're very inefficient because a lot of the model capacity and optimization effort is dedicated towards samples that will ultimately go unused. You basically, when you restrict the space or you reject samples, you've put model capacity and modeling effort into these garbage examples. And so instead of training a model and then rejecting samples, we propose to first reject training examples via the process of instance selection, and then go ahead and train the model. So it's a really simple flip on what's currently being done. But surprisingly, while people have looked at instance selection in supervised learning, nobody really had looked at this and evaluated it in the context of generative models. So in this way, when we do it this way, it's much more computationally effective because we can redirect model capacity towards samples that will actually be used. And it turns out that we can actually train much smaller or lower capacity models in a more reasonable amount of time when we take this approach. And so what led us to this work is we started looking at the relationship between data density and image quality. So we found that, you know, even though the mantra in machine learning tends to be more data is better, always get more data, there were certain low density regions in the training data manifold that seemed to be hurting models. So, you know, if you had a well-represented region given some training data, you could model that pretty well. But if you had sort of underrepresented areas, your model would attempt to capture that variability, but it would do a horrible job because GANs are still being perfected. They're not perfect models, and perhaps increases in technology for GANs, better GAN type models, this will abate this problem. But at the current state of the art, these low density regions seem to be hurting GAN models. And so in this very simple experiment, you see here, we generate samples with a pre-trained big GAN. So we flip through different classes. And so on the scatter plot, you're going to see one data point or one point in X and Y for each class. And so you've got about 1,000 classes in ImageNet. And then for each point, the x-axis is going to be its likelihood, negative log likelihood, using a Gaussian in inception v3 space. So you're going to basically put all of the images through inception v3, get these vectors, fit a Gaussian model, and then compute their negative log likelihood. And then on the y-axis, you're going to have the average FID, which is the Frechet inception distance for, and that's just a common image quality metric, the average taken over all the images of that class. And so we can see the relationship between density and quality. And so the claim here is that, you know, classes where you don't have sufficient density, if you're looking at the entire manifold, are leading to lower quality regions. And so this suggests, because these two are quite correlated, that we could do an approach motivated by instance selection and supervised learning, where we first project data into a representative feature space, like the inception v3 model I just mentioned. And then we have a scoring function that assesses the data manifold density for each example. And effectively what we do is we form a new data set where data that is from high density regions is maintained, but data that doesn't meet this density threshold is thrown away. And this happens prior to training. So just to give a visualization, what happens here, here's some training images. They're getting embedded into a task relevant feature space, such as that of a pre-trained classifier. We then go, we fit this density model to the embedded points, and we rank them according to their likelihood. And then all the data points scoring above some threshold are kept, and the rest are discarded. Okay, so we see that happening. And of course, we're going to get a fidelity diversity trade-off because we're throwing away data. But what we're particularly interested in is actually exploring this this trade-off as we control the degree of data retention. And so actually, we also have tested many different feature spaces and density models, and that's in the paper if you're interested in reading more. But we find that just an inception v3 feature space and a simple Gaussian density model work quite well, even when stacked up against more complicated techniques. And so there's a single hyperparameter, which is the amount of data to retain. So a retention ratio of 100, so that's the black line in these plots, means that we're not throwing away any data at all. A retention ratio of 10 means that we're only retaining 10% of the data. We're throwing 90% of the data away. And that's in the light yellow here. And so this experiment uses cGANs trained on 64 by 64 ImageNet for 500,000 iterations. And we measure different types of metrics. So we have metrics that are sensitive to image fidelity, like inception score, precision and density. We have metrics that are sensitive to diversity, like recall. And then we have metrics that are sensitive to both, such as Frechet inception distance and coverage. And so what we see is that for really low retention ratios, when we throw away too much data, we actually have the model collapsing during training. So that's where you see these peaks go up and then just fall and crash. So this is sort of that retention ratio of like 10, 20, and 30. But with a reasonable retention ratio, like 40 or 50% of the data retained, we actually see those models outperforming in terms of fidelity. So inception score is improved, precision is improved, density is improved. On models that are sensitive to both, like FID and coverage, we also see the models with a lower retention ratio outperform the full data counterparts. And again, like we're basically showing you, train your model and 40 or 50% of the data, it's producing higher quality results. And even on metrics that sort of trade off diversity and quality like FID and coverage. And so in the middle bottom is the recall plot, where you see that we are, of course, as obvious, we're trading off some diversity of the samples. And so, but if you look, these lines are fairly tight together. So our argument here is that we can achieve a higher fidelity with a minor trade-off in diversity, and that this trade-off is worth it. So here are some samples from those models, and we have our baseline model, which has no instance selection, and then a baseline model that has 40% of examples retained. And then we run a pre-trained Inception v3 classifier to detect the class of interest, which here I think is like goldfinch or something like that. And so you see that with the baseline, there's a lot of errors detected. Like majority of these images are not being picked up as goldfinch by the classifier, whereas in the baseline trains with instance selection, there's only one failure to detect. I guess it can't be goldfinch here because there's also, I think, sorry, there's two classes here. There's like a robin class and there's a goldfinch, top row and bottom row. And so you can also notice here the quality diversity trade-off, right? Like the examples on the bottom don't have as much diversity. You're not getting these scenes with no bird in it or cluttered scenes. But for the purposes of actually generating a diverse set of birds, I would argue that the images at the bottom look pretty reasonable. So let's scale this up. What about 128 by 128 ImageNet? We take a big GAN model versus with no instance selection versus a big GAN model with instance selection. And so what we do here is when we apply instance selection, this allows us to scale down the capacity of the model. And so using 8 V100s, we can train it in 3.7 days instead of 14.8 days. And again, on all the metrics that are measuring fidelity, inception score, FID, precision, density, and coverage, we're doing better than the baseline Big GAN, and we're trading off a little bit again on the recall or the diversity metric. So again, scaling up to 255 by 255 ImageNet. This is one of our most intriguing results. So this allows us to scale the model down when we use 50% instance selection, such that we have approximately 10 times less multiply accumulate operators. And so we can actually train a model that was normally trained on 256 tensor processing units, which we don't have access to in our lab, and very few people have access to a model that can be trained on 4 V100s in about 10 days. And so there's a message here about effectively making this kind of modeling at this resolution, 256 by 256, accessible to academic labs or not-for-profits or startups, ones that don't have the Google scale infrastructure. So basically, we've cut down half of the capacity. And again, on a lot of the metrics here, we're closely matching or outperforming the standard Big GAN model that doesn't use instance selection. So if you look at the generated images, using instance selection, we've got better image fidelity than the baseline GAN, even though it's using half of the trainable parameters. And in these examples, we actually see instance selection significantly improves the generation quality of fine details. So you look at the faces of the foxes and the red panda and the bear, look at their faces and then look at the faces on the left. Hopefully that's coming through on Microsoft Teams, but there's noticeable artifacts and problems with the faces of the animals here. So it's missing, the model that doesn't use instance selection is missing fine details such as facial features. And so as a result, we can generate photorealistic images for a wide variety of classes. And so let me summarize. So we've got some time for questions. And the first work that I talked about was Geneva. So we presented an iterative conditional GAN, which can draw complex scenes consistent with provided instructions. And we also introduced a relational similarity metric for assessing its ability to render objects and their relationships. So future work in Geneva would be scaling to realistic images. And I should say we are in the process of doing that. We have some work underway. It's not ready for publishing yet, but we're doing this in not just 2D, but 3D. And we'd also like to have an interactive drawer that asks disambiguation questions. And also, as I mentioned before, we'd like to have a model that can recover from its mistakes. I skipped over, in the interest of time, the middle work, but on the instance selection side, we've proposed this very simple method for improving GAN performance, which can trade diversity for improved sample fidelity, reduce model capacity and thus energy usage, and train models faster. And so what I didn't really tell you about, and I'll just show you the summary, is this other work that we've done that looks at how to evaluate conditional GANs. So there's metrics like FID that can capture visual quality. You can also run, like we did, an off-the-shelf object detector to see if you're asking for something in the conditioning, whether the object itself shows up, so you can measure conditional consistency, so consistency with what you're conditioning on. And then there's other metrics, like I showed, recall, that can capture diversity, or LPIPS, or other methods that have been proposed. And various papers evaluate these separately. And so we have another work that proposes this Fréchet joint distance. Again, it's very simple calculation, but it embeds the conditioning. You have an embedding for the generated image, and it looks at these embeddings jointly and helps us address potentially ambiguous trade-offs when doing model selection. You're not looking at 3 or 4 metrics, which are all telling you a different relative ordering of your hyperparameters, your model selection. You're looking at a single metric that tells you this is the model you want to use, or this is the setting of the hyperparameters that you want to use. So I didn't really get into the detail on that, but that's the other work. I'm happy to talk about it if there's more questions. But I think I'll leave it there, acknowledging the students that worked on this work. And then I also have references for you. All the work has been published, so you can check out the papers. Okay, so Mark, I heard your audio come back. I'll let you moderate.
Great, no worries. Thank you very much. We should have I've got an automated clapping sound, so we can have a better sense of that. Oh, okay. I think my mic is a bit of an echo here because of the way that my thing's set up, so I'll mute when I'm not talking. Yeah, I don't think we had that many people asking questions along the way. You really thoroughly covered some of the things that a concept will come up and then cover the background of it. I guess one of the later things that'd be interesting to talk a little bit, you said about this more efficient matrix setup of one of the calculations that lets you get by with different cards. That's really seems really important. I could probably apply to lots of different things. So was that particular to this very specific model you had, or?
Oh, no.
Is there a more general lesson there?
I mean, everything that we looked at was in the context of generative adversarial networks, but I think certainly this general idea of doing manifold-based instance selection would apply to other types of generative models. And so it remains to be seen how this actually plays out. But there's, sort of thinking on the fly here, I think there's very little that's GAN specific in terms of reducing the capacity of the models and therefore their compute usage. So yeah, I think there's a good story. Like many of you may have seen this Allen AI, Green AI paper from half a year ago. There's a good story here about sort of reducing the energy usage about in a space that's been particularly bad. I mean, people are just saying, should we really be running this much computation to generate pictures of cats?
Oh,
I guess
sure.
In this case,
yeah.
Right? Like in my case, it was like grizzlies, but like still, right? Like to what end?
Right. Yeah, you want graphs that have lines above other lines. That's the goal. But
Exactly.
With power we use to do that, and yeah, it's great that you're trying to apply to things that can really kind of make the world a bit better as well. We have a question from the audience on generating programs. So generating programs, do you think that's like, you're talking about generating images and things, but generating text, can you generate programs?
Yeah. So yeah, there is work going on in the area of program synthesis. And when I was on sabbatical in Montreal, the group at Google Brain Montreal had one team dedicated to generative program synthesis. So if you're interested in this area, you can look towards some people like Danny Tarlow, who is a PhD student at Toronto when I was there. He's now in that office. And he's leading a group which is doing really interesting work. So, I guess in some cases this is done well at big companies because they have internal software code bases and infrastructure and ways of doing things where you can have very fine-grained data captured at the level of, like, I don't know, they don't use Git there, but like imagine like Git commits. So if you have that very fine-grained control from tons and tons of software engineers, you can do very ambitious efforts. So anyways, I would point to that work. Definitely program synthesis is really interesting, and we're just starting to embark in a project with the Interchain Foundation that would look at automated software testing for distributed like sort of blockchain style software platforms and networks. And so that definitely intersects with program synthesis, generating automated tests and trying to detect failures.
Right, great. But yeah, that's a whole other area, but that's a really exciting too. Yeah. But I guess the main point of all your work is like, or at least what you're talking about here, is the importance of conditioning to make these things more efficient and more powerful. So do you think this is still an underappreciated area, like a method in ML in general?
I think so. Yeah, I mean, it's like reflecting on the title a bit and sort of doing this for 15 years, conditioning in different domains, from motion capture to text to images to Lego and so forth. And some of the commercial examples that I showed you, it's a pretty powerful mechanism. And I heard something really interesting at a vector talk yesterday. It was David Luis Lopez Paz. He was talking about there always being this sort of implicit conditioning when we train a machine learning model. So we're always conditioning on the fact that the data was observed, right? So he's talking a lot about sort of like out of distribution problems. But I thought that was a very interesting statement. Like, we're always conditioning, right? We always deal with very specific data sets that were captured in a specific setting. So yeah, in a sense, we're always conditioning, but the more explicit you can be about your conditioning, it gives you more control. And I didn't really talk too much about conditioning mechanisms. I sort of alluded to it. A lot of the work that we've done, other people are done, and like how does the conditioning information actually enter into your network? So it's things like film and conditional batch norm, which are really interesting, and other methods that people are proposing for this.
Right. Yeah. Well, that would be a whole other talk. So,
whole other talk. Yeah, exactly.
Okay. Well, I think that's the end of our time there, and
cool.
We'll thank you for your great talk, and people can kind of look at this stuff online and dig in and talk to you separately.
Yeah, thanks a lot. I got the references there on the screen, and yeah, I guess the last thing I'll say is, I've talked about generative models today, but there's a lot of things that my group's interested in, and we've always had a great time working with people at Waterloo. We're only, right now it's virtual, but in non-pandemic times, it's just a short drive away. So we're happy to chat with you and do projects together. And so if you want to learn more, there's my website and more about Care AI at Guelph. You're definitely invited to our seminar series as well. We've got some great talks, so please sign up to the mailing list and check it out.
Great. Yeah, so we can take a look at that, and we'll share that link up on our site and our Twitter. So thanks a lot, Graham, once again.
Super. Thanks, Mark. Thanks, everybody. And again, I'm really sorry to hear about Pearl's passing. So, as we go through the week, I wish you all well and grappling with this really sad news.
Thanks so much.
Bye-bye.
See you all next time.